Day everybody. Thank you for attending my lecture. My name is Mo King and I'm a theoretical cosmologist. Now, just one point, the name Mo is not short for Mohammed. It's a nickname ascribed to me many thousands of years ago during my apprenticeship. Or it seems like thousands of years ago anyway, that was a good time of my life, and I've happened to retain the nickname for all these years. Now, this is an unusual video in view of cosmology, because I've been working with cosmology for nigh on 30 years, and it's only in the last 2 or 3 years that I've been able to sort out many of the problems within the cosmology society of today. So initially, I'm just going to give you a quick preview of the items that I'm going to be discussing, and I may be looking at the side here because I have a crib sheet to help me to remember, because I have terrible problems with short-term memory. Right, now, the first point is going to be, I'll put it in a nutshell, gravity controls time. It may sound a little bit far-fetched, but it's true, and it's based on time dilation. Now, most of you people out there, if you have any sort of interest in cosmology, will understand the term time dilation. And basically, it's looked at as being when gravity gets stronger, as in a black hole, time slows down. But it goes a lot further than that, which I will pick up on in a few minutes. The next point is gravity lensing. Now, I'm going to discuss this a little bit more again later on, but it's one of the first phenomena that intrigued me and made me want to study the in-depth functions of gravity lensing. And to me, this is what cosmology is all about. And most of my findings have come about by my use of cause and effect. Everything that happens out in space, in the cosmos, has a cause and it has effect. If you don't know one, then sometimes you're able to work out the other, and vice versa. Right, the next one is quite important. Because gravity controls time, then we have a bit of a problem, because the way we measure gravity is the rate of fall of an object in the Earth's gravitational field. Hence, we have 10 meters per second, or to us oldies, 32 feet per second. Now, I can't really go into that too much, but the measurement of gravity may be very important later on, because I think what I'm going to come out with within this is going to be very important and very far, not far-fetched, but far-reaching in its applications and its effects. All right, the next one is another biggie. The speed of light is not, I repeat, is not a constant. The speed of light is a variable. I've got the birds agreeing with me now. They must be interested in cosmology. Right, I'm not going to dwell too much on that, because as I say, I'm going to go into these a lot more. Now, the other one that goes along with the speed of light is that photons, or light quantas, have mass. Now, I've heard many scientists on various documentaries tell us quite graphically that light doesn't have mass. Now, a simple answer there is, if light doesn't have mass, Why do we have black holes? A black hole is purely because light is held at bay by the tremendous gravity of a black hole that stops the light actually escaping. So that's the reason for light having mass, and there are others. Now this one is an anomaly within cosmology, and I would like to put a stop to it right now and for as long as it will stand it. And this is the fallacy that within Einstein's famous equation E equals mc squared, and m being mass, there are many people, certainly on the internet, that say as the energy level within that equation increases, so mass increases. And I can tell you right here and now, that is absolute and utter rubbish. That mass doesn't increase. The mass is inviolate. Now, it sounds like I'm double talking, but when you generate light from, say, a battery or from an electric current, you are creating light and you are therefore creating mass. So the mass really is created by energy. But as far as increasing mass through an increase in the energy of Einstein's equation, then no, definitely a no-go. It is not valid. Right, now, because of this variation in light speed, I've had to create the ultimate sin. I've had to change Einstein's equation. Now, don't get me wrong, I think the world of Einstein. He was a great man, and for his time, well, over 100 years ago, his ideas and his equations were absolutely fantastic, absolutely brilliant. So I won't hear a word said against him. However, although he knew about time dilation in those long distant days, he obviously didn't realise that gravity changes time. And because of that, he wouldn't know that light is not a constant, because in his day, everybody that had tried to measure light came up with the same constant speed, hence light being a constant speed of, and I will use my term for the speed of light, 300 megameters per second. I use that term because it sounds better and it's much easier to work with in calculations. Now, with that in mind, I've had to change the equation from E equals mc squared to E equals mv squared, whereas the v is the velocity of light, which being a constant covers all the velocities, whereas c is a constant. So just a minor change, but it has some long-reaching effects. And the first one I came across was the equation for kinetic energy, and it's very interesting. I will tell you what the equation is for those of you who can't remember it, and you'll see the connection between E equals mv squared for Einstein's theory with the new modification in it. And the equation for kinetic energy is kinetic energy, I'll usually write that down as E with a subscript k, equals half mv squared. Now, it's a bit of a coincidence, but now Einstein's equation with my modification reads E equals mv squared, and the kinetic energy is half mv squared. So to my mind, that immediately means that when you do any calculation with E equals mv squared, all you have to do is divide by 2 to get the true energy without taking into account the kinetic energy. So all the energy of movement is removed in one fell swoop. Now, That's the last item, and I'll go through those in a moment. The first item, gravity controls time. Sounds like a bit of a mouthful, but it's been proved time and time again. We know that the time dilation effect occurs, and that is, putting it in a different phrase, gravity controls time. If you go to a planet that has twice the gravity of the Earth, then time would pass slower. Not for you, because while you are in that gravity, you are controlled by the gravity field and by the time field so produced. Now, I call this a time frame, purely for the mental grasp of the effect. There's no such thing as a time frame, except in my mind, but it does make it easier to think through. Now, on this planet that has twice the gravity, you will be under 2G gravitational field effects, and therefore from an outside observer, and I'm careful to say an outside observer, then the outside observer would see your time frame as being much, much slower than his, depending on where he is. If he was on a 4G gravity field planet, then obviously he would see your time frame as being much faster than his. But if he was out in space, not on any planet, then his time field would be controlled by the average gravity that he encounters. So if the background gravity was, say, for example, 1/10 of a G, then his time frame would be much, much faster than your time frame, either on the Earth at 1G or on another planet at 2G or even a planet at 4G. Now, this change in time has also got far-reaching effects, and we have felt these effects, if you like, via the Hubble telescope. Now, as far as I know, the Hubble telescope is working quite well now. There was a period when it was first put up where it had major problems, that they have been sorted out, and we now have good working details from the edge of the expanding universe, and that's what I'm interested in at the moment, because Hubble's telescope has picked up a phenomena that many scientists don't really understand what is happening, and that is that time at the edge of the expanding universe is passing at a rate faster than the speed of light. It's nice to hear these birds, but these blackbirds are rather loud. Right, so we have time at the expanding edge of the universe running at a very fast rate as observed from the Earth. Now, the Hubble telescope, not sure how far up it is, but it will be under slightly different time frame than on the surface of the Earth, for the same reasons that gravity is controlling the time to a different level at the Hubble telescope. But for the moment, we can ignore that. So we are seeing the edge of the universe expanding very fast. And there is a very simple reason for that as well. And that reason is that the edge of the universe is expanding into a greater volume of space. Now, as that greater volume of space, well, that's all I need now, dogs start barking. Right, we have the universe expanding into a greater volume of space, so therefore the amount of matter within that area is reducing in density, or it's being diluted, whichever way you like to look at it. Now, when you reduce the density of matter, it's the amount of matter per cubic mile or cubic kilometre of space. That density is dropping because the same amount of matter is expanding into a much larger volume of space. Now, because the density of matter drops, then so will gravity. And as that gravity falls, so the time frame will speed up. Hence, at the edge of the expanding universe, you will have a much faster time frame, or an increase in time frame, than we have at the Earth. Now, that's the first item of gravity controlling time. It does have some repercussions. One that I've already mentioned is that we actually measure gravity with time. A known weight or known mass falling with regards to time. And really, I was going to say that that's no longer valid, but within our time frame, yes, it is valid, because that calculates the gravity in a 1g gravity, and you can work that out to very, very accurate levels because we are in a set time frame. Now, if we then continue looking from this time frame and we look at a distant time frame, say via the Hubble telescope, another planet that is smaller than ours, i.e. Mercury or Mars, then we would see things happening at a much faster time rate because of the change in time frame due to the difference in gravity. I was going to say this is a very heavy subject, but I don't think this is the time for puns like that, so I won't say it. Right, in general, that's enough on the gravity controls time side. Now we'll look at gravity lensing. Again, this is a very common effect in space, but it is a little bit disconcerting, certainly for me, again because of the repercussions. Now, you can find a dim distant star whose light has been travelling for God knows how many thousands and thousands of years, and during that period, hopefully it hasn't encountered any large gravitational bodies and has reached the Earth at the Hubble telescope, and that data will be valid. But if during that travel of that light, those photons or quantas of light, during those thousands of years, if that light path encounters any other large body, like a sun or even a black hole, then that light will be bent around that body. And yes, I know about the curvature of space, but in this case we're looking at the curvature of the light, because light does have mass. This is another evidence that light has mass. As that light bends around, so it picks up energy. Now, in the case of a rocket ship slingshot effect, then the rocket ship will be increased in speed. But with light, I was just going to say you can't increase the speed, but what happens is that the light changes time to use the extra energy that it's got for a limited period. And as that light continues on its slingshot effect, that extra energy builds up within that photon until such time as the energy equals just a fraction more than twice the energy of a photon, at which point a new photon will be produced. So you have two photons. Now, unfortunately, they are both exactly identical, right down to the data that has been, how can I put it, the data that is passed to the photon in the spectral shift. So if there's X amount of spectral shift in that photon, then the new photon will have the same spectral shift. So that new photon can then go off and it will go off at a different angle to the angle of the original one. The original one has obviously been bent out of position, so both those photons, when viewed later in time or viewed from that point where they just escape the effects of the gravity, then you will get an image of that far distance planet or solar system or galaxy, and that image will be displaced not only in angle but in distance. Now, this means that we cannot use light for measuring distance. The spectral shift, the blue and red spectral shift of light, cannot be used unless that light is or has reached us without encountering any other gravitational field. As soon as the gravitational field changes, then the speed of that light will change. So for that reason, we cannot use the red and blue shift of light pulses to calculate any distance. It's a pity, but there you have it. So that's one important point of light that we can't use. Now and there's a lot more to do with gravity lensing, but I won't go too deep into it. In effect, the reproduction of the light pulse can happen 5, 6, even more times, dependent upon the intensity of the gravity and the angle at which that light passes around that gravitational well. Now, these light effects can eventually escape at a different angle and go on through time, say for 1 million or more years, and then at some time or other encounter another heavenly body that has quite a large mass and be deflected again. And while it's deflected, it's going to pick up energy, and it can then reproduce more photons, but in a different direction. Now, how many times this occurs, I haven't got a clue. It could occur many, many times over the period of hundreds of thousands or even trillions of years. But what this produces is a problem, because it will produce the image of a star, not once, not twice, but possibly numerous times. Now, I can't swear to the validity of this, but certainly you can give it some thought. When we look up at the sky at night, we see all these, well, literally millions of stars. But how many are really there? And how many are celestial prints, if you like? I'll leave you to think about that one. Right, and the next point, gravity is used to measure time. I'm not sure about that. Oh, I put that for gravity is... Oh no, gravity is measured using time. Sorry. This is my short-term memory giving me problems. Gravity is measured using time. How do we get round that? Because we use time for measuring the distances that light has passed through the cosmos, so we can't use that method anymore. I think the only thing we can use is gravity, because gravity seems to be unaffected by nearly everything except distance. Gravity is not affected really by time, because gravity controls time. So gravity is only affected by distance, and we have an equation for that, because gravity, once it's left its source, drops off at the rate of the inverse square law. So if we receive a gravitational effect on the Earth, let's say from a black hole, then we should be able to reverse calculate that and work out from the actual received level of gravity, work out what the actual source gravity is, and that will give us a distance, obviously. That is the only thing I can see that we can measure distance with without using light, which means using a variable time. So it causes us many problems, but I hope no problems that we can't overcome. Right. Now the other thing, the speed of light is not a constant, which has made me change Einstein's equation to E equals mv squared. Now, I only just touched this subject earlier on, but let's take a number of planets. We got Mars, which I think, can't remember the actual gravitational level of Mars, but it's lower than the Earth. And then we have Mercury, which I think is 3/8 the gravity of the Earth. So time on Mercury, Mars and the Earth are all running at different times. But if you are in any one of those time frames, then you will be subjected to that time within that time frame. So if you tried to measure the speed of light while you were personally in that time frame, then that would come out at 300 megameters per second. And there is a reason for this, and the reason for it is the photons or quantas of light have mass. Now, because the light has mass, it's affected by the gravitational field that it's in, or the time frame that it's in. And therefore, the speed of light is going to be set by that mass. And that is controlled by the gravity field that it's in. So you've got almost like a double effect. The time frame is set by gravity, and the speed of light is set by the mass of the photons. And because the mass of a photon is constant, then it seems as though the speed of light is constant. But if you then view all your findings from a different viewpoint, and if that viewpoint or the observer is outside the effects of your time frame, then you will get the differences. So time is shown then to be a variable. And as I say, it's important to take into account the effects of mass within the pulses of light, because that is what affects the limit to the speed of light. Now, if we then move to a position where gravity is very low, I won't say any particular field, but the gravity is very low, and if we are in that gravitational field, then we will see the speed of light as 300 megameters per second. Okay? Now, if we then observe that same effect from the Earth, where we are under the constraints of 1g gravity, and therefore in our terms the speed of light will be affected by 1g of gravity, and therefore light will be 300 megameters per second. But when we look outside our time frame, at a point in space where the gravity is much lower, then we will see and we will measure and we will confirm that light does indeed travel much faster, a lot faster. And as I've said before, this is the reasons for the view of the edge of the expanding universe seemingly speeding up. Now, the reason I gave this a lot of thought is because when I first heard about this speeding up of the fringe of our expanding universe, I just turned around and said, that is absolute rubbish. It just can't occur, because there's not enough latent energy within the universe to move the whole of the universe, making it expand faster than the speed of light. And the phenomena is an actual fact. But it's not the universe that is expanding at the speed of light. It is the changing of the speed of light due to gravity. Because, again, gravity controls time. And it's gravity that affects the speed of the expansion, and that expansion is in, if you like, a low gravity area of the cosmos, and therefore everything is happening much, much quicker. That's the speed of light. I've already explained to you that photons have mass. Now, I won't show you my calculations because I got a little bit screwed up with some of them, and so I have nothing that is really legible to show you. But during my calculations, I found out that each photon, once we removed the kinetic energy, and I did the calculations for white light, which is obviously a range, and that range was between 2 and 5 times 10 to the minus 36 kilograms. 2 to 5 times minus 36 kilograms. Now that is a very, very small amount of mass, but that is what came out in my experiments, or rather my mathematics, which I might add is my maths is not very good. I didn't actually do much in the way of maths, and most of my mathematics now has come from my deep interest in cosmology. Right, so photons have mass, and it's important that we keep that in mind, because many scientists again say that photons do not have mass, and I heard one scientist say, "I can state categorically that light does not have mass." Well, I'm afraid I can just laugh at that, because the universe wouldn't do what it does, and does so well, without having mass. So I'll leave that for one moment. The other point, that mass increases with energy, again I'll reiterate that when you increase the energy into Einstein's brilliant equation, mass does not increase. Mass does not increase. What increases is the kinetic energy component, which I've just explained, but the actual mass is sacrosanct. It does not increase. The only time that mass can increase is when we generate light, and the energy is used to generate set amounts of mass for each photon of light, or each quanta of light. Again, very, very important. Now, the kinetic energy, I've already explained that, but I'll just go over it briefly. It's important to understand, because there's a difference now that I've altered Einstein's equation to read E equals mv squared. So we have kinetic energy, which is E kinetic is equal to a half mv squared, which is half of the energy for Einstein's equation. So we don't have to worry about the equation, as long as we know that when we do our calculations, we can just halve the result, and we've got the amount of energy without the moving energy, kinetic energy applied. And it's using the equation in this way that gave me the mass of the photon that I obtained. Now, what else is there? Just one little thing that made me really think. What would happen, or what would the effects be, if we were to invent a machine, let's say it's quite small, it doesn't need to be big in our imaginations, does it? Let's say we invented a small machine that we could turn a control and reduce energy from, not energy, reduce gravity from its normal level down to zero. Now, if we had a platform and we wanted to reduce the gravitational pull on that platform to zero, so that platform would then float, great idea if it works, and it would work. But there is another outcome of that, because gravity controls time, and if we were to gradually turn that control down to reduce gravity to zero, we would gradually increase the time of the time frame of the platform and all that is associated with it, and that would be the pilot, if you like. And we would all find that time passes very, very quickly for us. So by looking out the window, we would see Earth gradually stagnate. I don't know how the Earth would change over 1,000,000 years, but we would see that change in just a few milliseconds, if you like, because time outside would be slowed right down, whereas our time would be going very, very, very quickly. So we would see time changing on the Earth, I don't know, 1,000,000 times a second of what it is now. So for that reason, if you then stopped your machine and turned it back to full gravity, you wouldn't return to the Earth that you knew, because possibly 1,000,000 years may have passed for you, depending upon how long you stayed within that. Well, it's not quite a zero gravity, because there's another point with that. Zero and infinity, they occur in mathematics, but they are only valid in mathematics and cannot be used to calculate reality, because in reality zero and infinity does not occur. If anybody tells me an infinite number, all I need to do is add one, and that infinity number is then no longer infinity. It's infinity minus one. So, and the same applies to zero. You can never ever get down to zero. You can take 99.999 sand grains away, but there's always a fraction of a grain left, and you can halve that or you can reduce it by 1,000, but that zero is never absolutely zero. So for that reason, zero and infinity cannot exist in reality, and we need to show that in our mathematics, because I've heard a number of scientists, and one, I can't remember his name, it's I think he's a Japanese scientist, getting on in years like I am, and like me, he has white hair, but he's grown it long in long flowing tresses, and he was complaining that a lot of his mathematics, and I'll say he's much better at the maths than I am, but he was complaining that the results were coming out to zero and infinity, and that's because the two don't really exist in reality, only in the mathematics. Now, I'm going to draw a stop on that now, and this will be the end of this first cosmology video. The next one, and I've got to produce this, so it's going to take me a bit of time. Now, I don't have any of the facilities of these big institutes or universities. I have no affiliation to any other society, institute or company or university. I am my own person. The only thing I'll say is most of what I've gone through at the moment sounds very far-fetched, but each piece falls exactly in its place, almost like a puzzle, and all the pieces fit together and the whole lot works together. So there must be a lot going for it. Now, the second video will be about the build-up of a black hole from the start where it's a large sun right through to the death of the black hole. Now again, I hear many scientists say we don't know anything about the inside of a black hole because physics doesn't apply there and we don't understand the conditions inside. Well, I'm afraid, again, I would say that's nonsense, because we do understand it. Nothing changes because a fictional area around a star that we call the event horizon occurs. The event horizon is nothing that is actually physical. It's just a distance from the surface of that sun that is calculated by the actual gravity of that sun, and when that gravity gets to a certain level, so light cannot escape, and it's that position all around the sun, a sphere if you like, and every point on that sphere the gravity is the same and light cannot escape. So when viewed from space you would see a black ring, but the big difference is from any point in space you would see that black ring, because that is in effect a black sphere. It's spherical, so any matter that falls into that black hole can fall in from any direction whatsoever. Now I won't go too far into that because I'm saving most of the effects for this next video, but the physics that I'm using are the standard physics of cosmology, and they all still apply, because a large sun, plenty of large suns have been investigated. They know how they work, they know how they implode, how stars change into a white dwarf and explode. We know how this all works. Now, why should that knowledge change just because there's a fictional area around that sun where the gravity is such that light cannot escape? We still know how it all works inside. We know what the gravity does. We know the effects of the gravity. And what I'm trying to do in the next video is to take all these effects right through from the birth of the sun, or the birth of the black hole if you like, right through to a super black hole where the energies are so large that the black hole actually ruptures space-time. And when it does that, I will explain later on in the next video what happens then. So just to whet your appetites, that is the sort of thing I'll be going through in the next video. So for now, I'll say goodbye and thank you very much for those of you who had the patience to listen through I know some of you are going to call them ramblings, but I think if you look into them and try and prove them wrong, I think you will find out that you cannot do it. So for now, goodbye, and thank you all for listening so carefully. Goodbye for now. Bye-bye.